So this is question 1C of the 2017 Level 3 Probability Concepts practice exam from Term 3, and this is the NZAMPS task. So in a parent survey, 46% do not have high incomes. For parents who do not have high incomes, 23% voted for girls to be allowed to wear trousers. For parents who have high incomes, 35% voted for girls to be allowed to wear trousers. Okay, 3 parents are attending a function at school, and in their discussion indicate that they all voted for girls to wear trousers. What is the probability of this happening? State any assumptions that you make and how reasonable it is to make these assumptions. Alright, so what we need to do is we need to firstly decide which sort of probability diagram is going to be easiest to represent this information on. Okay, so to decide on that, I want to show you a flow diagram that I think is useful. And here it is. So the first thing we need to ask ourselves is, are there 2 category variables or 3 category variables? By category variables, here's what I mean. By category variables, I mean a question which decides which category they're in. So whether they have high incomes or not is a category variable. Another category variable is whether they voted for girls to be allowed to wear trousers or not. So that's 2 category variables, and there's no third one in there, is there? So that means we're on the left-hand side, 2 category variables. If there were 3 category variables, we'd either need to use a 3-way Venn diagram or a tree diagram. With 2 category variables, we're either using a 2-way table or a tree diagram. We can use a 2-way table if all the numbers provided are counts or proportions of the total. However, if some of the numbers provided are conditional ones, that means probabilities out of a subgroup, then we need to use a tree diagram because it's difficult to show them on a 2-way table. So, let's have a look. So, 46% do not have high incomes. That's out of the whole lot, so that's not conditional, that's out of the total. But then when we get to the next line where it says, for parents who do not have high incomes, 23% voted for girls to be allowed, that is a conditional probability. Because, why? Because it's only out of those parents who do not have high incomes. So it's conditional on not having high incomes. So that's a subgroup, isn't it? The subgroup of parents who don't have high incomes. And similarly, in the next paragraph there, for parents who have high incomes, 35% voted for girls to be allowed. That's conditional too, isn't it? And that's out of the subgroup of parents who have high incomes. So therefore, because some of these numbers are conditional probabilities, that means out of subgroups, that means we need to use what? We need to use a tree diagram. So, when we draw up our tree diagram, we want to start with the variable that is out of the whole lot, where the probability is out of the whole lot. And so because we're told that 46% of the whole lot have high incomes, that's not conditional, it's out of the total, that's the first set of branches we're going to split it into. The conditional probabilities always go on the second split. So the first split is high incomes versus not high incomes. And so we want to put that in, and then we're going to label the probabilities of that on the branches. So 0.54 and 0.46, because we know that 46% do not have high incomes. Okay, and remember they've got to add to 1. At each split of the branch, probabilities have to add to 1. Notice that I haven't labelled them as percentages. I've used decimals. Never label things as percentages on tree diagrams. The reason why is that then when you come to multiply them, if you multiply whole numbers, which is what the percentages will be, or what they can be, then it's not going to work. So you've got to have them as decimals or as fractions. Okay, now, of those who have high incomes, we have whether they voted yes to girls being allowed to wear trousers, or whether they voted no. And we know that of those who had high incomes, 35% voted yes. And so, how many? What must be the proportion who voted no? So it's going to be the other 65%, isn't it? So 0.65. Again, writing it as a decimal. Now, amongst the not high incomes parents, what proportion voted yes? 23%. And so the other 77% must have voted no. Okay. Now the question is asking, if 3 parents are attending a function at school and in their discussion indicate they all voted to allow girls to wear trousers, what's the probability of this happening? State any assumptions. So, first of all, when we're asked a question about 2 or 3 things, 2 or 3 events combined, the simplest way to start is by taking one of them on its own. So, for one parent, we want to work out the probability that they voted yes. Now, if we look at our tree diagram, there's 2 scenarios where a parent could have voted yes. What are they? And we should tick them on the branches. Well, they're the parents that are high income and vote yes, and then the parents that are not high income and vote yes. So there's 2 ways that can happen. So let's start by working out the probability that a randomly chosen parent is high income and votes yes. And we would write it like this: high and yes. So how do we work that out? Well, when we go along the branches, we multiply. So it's going to be 0.54 times 0.35. And on a calculator, we do that, we get 0.189. Now we need to do the same thing for the other scenarios. So those who are not high incomes and vote yes. So that's going to be not high income times the probability of voting yes if you're not high income. So along this path here. So 0.46 times 0.23, and we get 0.1058. So now what do we want to do with those 2 probabilities? Well, to get the total probability that a parent votes yes, we need to add those probabilities together. So, for one parent, the probability of voting yes, and see how I'm labelling it as I go, is going to be 0.189 plus 0.1058. And so if you add them on your calculator, what do you get? Here we go. And I got 0.2948. Okay, in other words, 29.48% of parents voted yes to the new trousers. Right, now what? Well, I want to work out that probability for 3 parents. Now, when we're talking about combining events for multiple events, so 3 parents all doing the same thing, we multiply. That's assuming what? It's assuming that those events are independent. So we'll talk about that in a sec, but in the meantime, we want to multiply 0.2948 by itself, and then by itself again. So for 3 parents, the probability that all 3 vote yes equals 0.2948 to the power of 3 cubed, and that gives us what? 0.0256 to 3 significant figures. And so writing that down. So in other words, there's about a about a 2 to 3% chance, 2.56% chance of that happening. Okay, what does this assume? Well, the first thing it assumes is independence. We're assuming specifically that the votes of these three parents were independent of each other, which may not be the case. Why might it not be the case? Well, if they're friends or acquaintances who discussed whether or not they think girls should be allowed to wear trousers before voting, then they could have influenced each other's vote. So it's assuming that's not the case. The second assumption, which not many people think of, is that we're assuming that there are enough parents in total that the sampling of these three without replacement doesn't change the probability of each one voting yes by much. What does that mean? Well, here's an example. Say there were only 10 parents, so a very small sample, and then say the probability that they voted yes was 3 out of 10. So then the first parent that we picked would be a 3 out of 10 chance of voting yes. Three parents who voted yes out of 10 parents, so a 30% chance. But then after that, when we went to choose a second parent, the probability that that parent voted yes as well, we'd have to work out, well, there's only 9 parents left, and only 2 of those left voted yes. So it'd now be 2 out of 9 instead of 3 out of 10, which is quite different, isn't it? So that would make quite a difference, and it would mean that you couldn't just get the right answer by going to the power of 3. It wouldn't be 3 out of 10 cubed, it'd be 3 out of 10 times 2 out of 9 times 1 out of 8. Now, however, if we had, say, 1,000 parents with the same percentage chance of voting yes, so say out of 1,000, 300 voted yes, 30%. Then after you pick the first parent, it wouldn't change much. It had just changed from being 300 out of 1,000 to 299 out of 999. And then for the third parent, 298 out of 998. Not much different. So we would get a similar answer there to what we'd get if we went to the power of 3. Wouldn't change it much. So that's the second assumption, is that we have a large enough group of parents that the sampling without replacement doesn't change the probability much. Okay, that's the end of this video. Catch you later.